This is a simple test of Newton's second law of motion. I use the video analysis software Physics Toolkit available on Bob Carlson's website. I'll put those details up at the end. I'll also provide a link to a more comprehensive examination of the second law if you're interested. Here's the apparatus. We have a cart sat on an air track, attached by a piece of string to a hanging mass. That's all there is to it. If I press the play button, you can see how easily it works. Well, let's analyse it. Remember what we're trying to do. We're trying to get a force to produce acceleration, and we're going to test out whether F equals ma really works in the real world. What about the force first? Let's look at the cart and examine the forces on the cart. We have the downward force of gravity, of course, the weight of the cart. And balancing that perfectly, we have the normal reaction force supplied by the air track. As the cart is moving on an air track, we have minimized friction. As the pulley is a high quality pulley, it means that there is minimum friction there too. The only sideward force will be the sideward force produced through the string by the hanging mass. As you can see here, the hanging mass is 0.025 kilograms. By using this equation, we can calculate the weight of the hanging mass. In other words, what is the force of gravity pulling down on the apparatus? This is the unbalanced force. Now we have to be very careful with the next part. We need to know the mass that's being accelerated. If you said it's 0.15 kilograms, you fell into the trap. In fact, we must consider the hanging mass and the cart as one piece of apparatus. When they start to move, they move together, and it's the weight of the hanging mass only that produces the acceleration of the whole apparatus. So we have to consider the total mass, the cart plus the hanging mass, when we use our equation. Now we're ready for the experiment itself. Let me remind you what happens. That's the experiment captured on video. What we have to do now is analyse that motion. I'm going to do that by marking the position of the cart on every frame. That's every 1/10 of a second. And so on right to the end, like this. That's every position marked. So we have position, time, data. We can ask the computer to use that data to plot us some graphs. First we'll look at the displacement time graph. As you can see, it's a nice curve indicating acceleration. What we need to look at next is a velocity time graph. We'll ask the computer to do that. And there it is, a nice straight line indicating constant acceleration. In order to calculate the acceleration from a velocity time graph, you need to calculate the gradient. The computer will help us do that. Click on slope, down come the instructions, and I go from this end, and then click on this end. That's right. Oops. And there we have an acceleration of 1.39 meters per second per second. We need to see how that stacks up with F equals ma. What did F equals ma predict at the beginning of the experiment? The unbalanced force, or the net force, was equal to the weight of the hanging mass. That equals 0.245 newtons. The total mass is the mass of the cart plus the mass of the hanging mass is 0.175 kilograms. If F net equals ma, then the acceleration is equal to 1.4 meters per second per second. That's a pretty good agreement. So the theory F equals ma matches closely with the experiment. And you have to bear in mind that our experiment relied on my eyesight, which is not quite as good as it used to be. For a first effort, that wasn't bad at all. Perhaps we should look for some more experiments to test F equals ma a bit more rigorously. We'll do that in another video. Bye for now.